drop a stone, it falls. It's the first thing you learn as a child. Things fall down. We built our entire understanding of reality on this simple fact. We call it gravity. We call it a force. We say the earth is pulling you down right now. We say the sun pulls the earth. But here is the twist that will change how you see the universe forever. None of that is true. Gravity is not a force. You are not being pulled down. In fact, if you are sitting in your chair watching this video, you are accelerating upwards. Tonight, we are going to explore one of the most fundamental aspects of reality. We are going to peel back the illusion that Isaac Newton cast over the world 300 years ago. And we are going to stare directly into the terrifying, beautiful truth of general relativity. This isn't just physics. This is the story of why you are here, and why reality is nothing like you think it is. To understand the truth, we must first understand the lie. In 1687, Isaac Newton published the Principia. It was arguably the most important scientific work ever written. Before Newton, the universe was a chaotic place. People thought the rules that governed the heavens, the stars, and planets were completely different from the rules on Earth. Newton changed everything. He unified them. He gave us a law, the law of universal gravitation. He said that every object in the universe attracts every other object. The Earth pulls you. You pull the Earth. The Sun pulls Jupiter. And the math was beautiful. It was precise. It explained the tides rising and falling. It explained why planets move slower when they are further from the star. It was so accurate that in 1846, when astronomers noticed Uranus wasn't moving exactly right, they didn't doubt Newton. They trusted the math. They calculated where a hidden planet should be to cause that wobble. They pointed their telescopes at that exact empty spot in the sky. And there was Neptune, right where the math said it would be. For over 200 years, humanity thought we had solved the puzzle. Gravity was a force, a tether connecting all matter. But there was a crack in the foundation. A tiny, nagging problem that refused to go away. The closest planet to the Sun wasn't behaving. Its orbit wobbled it, precessed just a little bit too much. Specifically, 43 arcseconds per century, more than Newton predicted. It was a microscopic error, less than 1/80th of a degree per century. But in physics, a small error is a screaming alarm bell. Scientists tried to fix it. They invented a ghost planet called Vulcan to explain the pull. But Vulcan didn't exist. The problem wasn't a missing planet. The problem was Newton himself. Enter Albert Einstein. In 1915, he didn't just fix Newton's math, he destroyed the concept of gravity entirely. Einstein had what he later called the happiest thought of his life. Imagine you are in an elevator. Suddenly, the cable snaps. Terrible scenario, I know. But freeze that moment. As you fall, you float inside the elevator. If you drop your keys, they float next to you. You feel weightless. Now, imagine you are floating in a rocket deep in space, far from any stars or planets. You are also weightless. Einstein realized something profound. These two states are identical. This is the equivalence principle. If you were locked inside that box, no experiment you could conduct would tell you if you were falling toward Earth or floating in deep space. And if those two states are the same, it means something terrifying. It means that when you are falling, you are not being acted upon by a force. You are simply returning to your natural state. In general relativity, falling is the natural state of motion. When you jump off a diving board, for that brief second, you are free. You are following the straightest possible path through the universe. So, why do you feel heavy right now sitting in your chair? Because the chair is pushing you. The floor is pushing you. You are trying to fall toward the center of the earth. That is your natural path, but the ground is in your way. What you call gravity is actually the sensation of the electromagnetic forces of the ground accelerating you upwards, preventing you from following your natural path. You are not standing still. Physically, relativity says you are accelerating. But accelerating through what? To understand this, we have to look at the stage where the universe performs. Before Einstein, we thought space was just an empty box, and time was a steady clock ticking in the background. Space and time were separate, rigid, and absolute. Einstein shattered that box. He showed us that space and time are woven together into a single, four-dimensional fabric called spacetime. And this fabric is flexible. Matter tells spacetime how to curve. Spacetime tells matter how to move. This is the famous rubber sheet analogy. You've probably seen it. A bowling ball on a trampoline curves the surface. If you roll a marble nearby, it curves toward the ball. It looks like the marble is being pulled, but it's not. It's trying to go straight. It's just that the straight line has been bent by the mass of the bowling ball. Earth curves spacetime. You are trying to slide down that curve. But be careful. The rubber sheet analogy is useful, but it's a lie. Because the rubber sheet only bends space. Gravity is not just the curvature of space, it is the curvature of time. This is where it gets strange. The stronger the gravity, the slower time moves. Your head is slightly older than your feet. The core of the Earth is functionally years younger than the surface. This isn't a metaphor. It is measurable. If you use GPS on your phone today, you are betting your life on Einstein being right. GPS satellites orbit high above Earth, where gravity is weaker. Time moves faster for them than it does for us, about 38 microseconds faster per day. If engineers didn't program Einstein's equations into the satellites to correct for this time difference, your Google Maps would be off by kilometers within a single day. The global navigation system would collapse. Gravity is quite literally the warping of time itself. But if gravity is the bending of the entire fabric of the cosmos, why is it so pathetic? Look at this magnet. A tiny fridge magnet. It can pick up a paperclip. Think about what just happened. The entire Earth, all 6 septillion kilograms of it, is pulling that paperclip down. And yet, a tiny piece of magnet defeats the entire planet effortlessly. Gravity is 39 orders of magnitude weaker than the electromagnetic force. If you stand 1 meter away from someone, the gravitational attraction between you is less than the weight of a single bacterium. This weakness is one of the deepest mysteries in physics. Why is gravity so shy? Some theories suggest that gravity is actually incredibly strong, but we only feel a tiny fraction of it because it is leaking into extra dimensions we cannot see. String theory suggests there might be 10 or 11 dimensions, curled up so tight we can't notice them. Gravity might be the only force that can travel between these dimensions. But while gravity is weak here on Earth, there are places in the universe where it stops being polite. Places where the curvature of space-time becomes infinite. Places where reality itself breaks down. When a massive star dies, it collapses. If it's big enough, nothing can stop it. Not atoms, not neutrons, nothing. The mass crunches down into a single point. The fabric of space-time doesn't just bend, it rips. Gravity is usually a gentle architect. It builds solar systems. It holds atmospheres. But when gravity wins completely, it creates a monster. A black hole. Most people think of it as a cosmic vacuum cleaner, sucking everything in. That is wrong. A black hole doesn't suck. If our sun was suddenly replaced by a black hole of the same mass, Earth wouldn't fall in. We would keep orbiting exactly as we are now. The danger isn't the suction, the danger is the geometry. A black hole is a region where the fabric of space-time is curved so severely that space and time swap roles. At the center lies the singularity, a point of infinite density, a glitch in reality, where the laws of physics divide by zero and break down. Surrounding it is the event horizon, the point of no return. Imagine you are falling toward it. Crossing the event horizon doesn't feel like hitting a wall. You wouldn't even notice you crossed it. But once you do, your destiny is sealed. Inside the horizon, all possible paths through space lead inward. Trying to use your rockets to escape would be like trying to run backward in time. You cannot avoid the singularity any more than you can avoid tomorrow. The singularity is no longer a place in space. It is an event in your future. But here is the most mind-bending part. While you fall in, your friend, watching from a safe distance, sees something completely different. As you approach the horizon, time for you begins to slow down relative to them. To your friend, you never actually cross the horizon. You just get slower and slower. The light coming from you turns red. Redshift. Fades to infrared. Then radio waves, until you simply freeze. To the outside universe, you are frozen in time, forever at the edge of darkness. But for you, you look at your watch. Tick, tock, normal speed. You fall right through the horizon without stopping. You witness the universe outside speeding up. You might see the entire future of the galaxy play out in fast forward behind you before you hit the center. Relativity creates two different realities for two different observers, and both are true. But you won't live to enjoy the view, because of something physicists actually call spaghettification. Yes, that is the technical term. Remember, gravity is the curvature of space. Near a black hole, this curvature changes violently over short distances. If you fall feet first, the gravity at your feet is drastically stronger than the gravity at your head. The difference stretches you. Your body is pulled into a long, thin strand of atoms. Your bones dissolve. Your blood turns into a mist. You become a stream of subatomic pasta flowing into the void. For decades, these were just equations on paper. Einstein himself thought they were too strange to be real. But in 2019, we did the impossible. We took a picture of one. The Event Horizon Telescope, a network of dishes spanning the entire Earth, captured the shadow of the supermassive black hole in galaxy M87. That orange ring is light itself, bending around the curvature of space-time, trying to escape but getting trapped in orbit. We are looking at a monster 6.5 billion times the mass of our Sun. It is real, and it is waiting. Black holes don't just sit there. Sometimes they collide. In 2015, the LIGO detectors in the US picked up a signal, a chirp. It was the sound of two black holes merging 1.3 billion light-years away. When they collided, they released more energy in a fraction of a second than all the stars in the visible universe combined. But they didn't release it as light. They released it as gravitational waves. Ripples in the fabric of reality itself. Space squeezed and stretched. For a brief moment, you got a tiny bit taller and a tiny bit thinner. The universe rang like a bell, and we heard it. We have opened a new sense. We are no longer just looking at the universe. We are listening to the vibrations of space-time. But there is one final mystery. one that makes black holes look like child's play. Something that makes up 68% of the universe and is tearing it apart as we speak. Gravity wants to pull everything together. It wants to crush the universe back into a single point. For a long time, we thought gravity would win. We thought the universe would end in a big crunch. But in 1998, astronomers looked at distant supernovas and found something terrifying. The universe isn't just expanding, it is accelerating. Something is pushing space apart, faster and faster, fighting against gravity. We call it dark energy. We don't know what it is. It might be a property of space itself, but we know it dominates everything. Dark energy makes up roughly 68% of the universe. Dark matter is about 27%. The stuff you can see, stars, planets, you, me, is only 5%. We live in a universe where 95% of reality is a total mystery to us. And because of dark energy, gravity is losing the war. As acceleration continues, distant galaxies will be pushed beyond our cosmic horizon. They will move away from us faster than the speed of light. Their light will never reach us again. In the far future, trillions of years from now, the universe will be a lonely place. Civilizations born in that era will look up and see nothing. Only their own galaxy. They will have no way of knowing the Big Bang ever happened. They will think their galaxy is the entire universe, surrounded by infinite void. We are fortunate. We live in the brief golden age where we can still see the history of the cosmos. But it gets worse. Eventually, stars will stop forming. The fuel will run out. The universe will go dark. Black holes will be the last survivors. They will reign over a dead cosmos for eons. But even they are not immortal. Through Hawking radiation, black holes will slowly evaporate. One by one, they will vanish. The universe will be left as a sea of cold photons and elementary particles, floating in ever-expanding darkness. This is the heat death, the ultimate end of geometry. It sounds depressing, doesn't it? Because right now, we are here. Think about what you are. The carbon in your cells, the iron in your blood, the calcium in your bones. Every atom in your body was forged in the core of a dying star that exploded billions of years ago. You are not just in the universe, you are the universe. You are stardust that has come alive to look back at itself, and you are living in a universe of curved spacetime. When you sit in your chair, remember, you are not static. You are traveling through time. You are interacting with the fabric of reality. You are surfing the geometry of the cosmos. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." We are tiny creatures on a small rock, yet we have measured the bending of light. We have heard the collision of black holes. We have figured out the rules of the game. So, the next time you drop something, don't think of it as falling. Think of it as finding its natural path, and realize that you, too, are following your own geodesic through this beautiful, strange, and curved reality. Thank you for watching. If this journey through space-time shifted your perspective, consider subscribing. It helps us explore more mysteries together. And tell me in the comments, does the idea of the heat death scare you, or does it make this moment right now feel more precious?